Hello folks. In this lesson we're going to take a look at a bunch of different functions and their graphs, and we're going to discuss how we can quickly graph them without having to create a really long table of values. We're going to focus on some key points for each one, and that'll make the graphing of these a lot faster. The idea here is, I know there's graphing software out there like Desmos that can graph things very quickly, but to be able to do really advanced mathematics, I think one of the expectations is that students can look at an equation and actually see what the graph is going to look like almost in their mind to be able to formulate the shape of it. And this is going to start that practice so that you can do that. We're going to start with a couple of functions that you already know. We're going to start with a linear function. And if you think about the general linear function, f of x is equal to x, which is in the style of mx plus b. The m, which is your slope, would be a 1 in front of the x, and the plus b would be 0. So knowing mx plus b allows us to graph this very easily. But if we wanted to do it from a table of values, what would be the least amount of points that we would need to know exactly what this graph kind of looks like and what its behavior would be? So I always like to use a negative number, 0, and then a positive number. So for my x values here, I'm going to use negative 1, 0, and 1. And because y is equal to f of x, as we've seen recently, I just substitute the x value, negative 1, into the equation for the x value. X would be negative 1. So f of x, which is your y value, would also be negative 1. That carries for the next 2 points as well. Now I have an idea as to what the graph looks like on the negative side of the x-axis at 0 and on the positive side of the x-axis. So if I plot those points, that's what I'm going to get. And my graph is going to be a straight line, as we already knew, going through those points. So this is a really easy one to get us started to think about how we're going to generate a table of values, and like I said, the most efficient table of values. Like, what's the least amount of points that we would need to know what this graph looks like? For the domain and range, once again, there are different formats for domain and range. The one that we're using in class, we're going to set up our interval. Well, this graph exists, and if I put the arrows at the end of it to show that it's going forever, this graph exists everywhere along the x-axis. So as I go to x equals 1, there's a point on the graph. X equals 2, there's a point on the graph. X equals a billion, there's a point on the graph. So this graph exists everywhere. So the proper symbols for that is x to the element of r. And the same thing is for the y-axis. No matter where I go on the y-axis, there's a point on the graph somewhere to the left or right. So we would write f of x as an element of r as well. Moving down to our next curve, you'll recognize this as a quadratic. Once again, what is the minimum amount of points that we would need to be able to draw our quadratic? Well, in this case, because a quadratic is not linear, we'd want to go a little bit further than just negative 1. What I normally do is I go to negative 3 all the way to 3. And leave myself a lot of room here. And the reason I do that is because to find the f of x value, we're going to be squaring the x value. So if I substitute negative 3 into x squared, negative 3 squared is 9, and then it's going to be 4, 1, 0, 1, 4, 9, which some people call a step pattern. And the reason I want to do that is because you're going to get your curvature of your quadratic by plotting those points. And if you don't plot enough points, you're not going to see that curvature. Now, it's really hard for me to do this on my tablet here, so I'm going to give it a shot. That should be a continuous line. And there's your parabola. So if you hadn't gone to -3, if you had just gone to -2, you might see enough of the curve to be able to draw the parabola. But going to -3 to +3 really helps us see that. And again, this graph does continue forever. So when I write its domain, it's going to be actually similar to the domain for linear because it does exist on every x value. For the range, however, we have a limiting value here because the graph only exists above the x-axis, so greater than or equal to 0 in the y values. So f of x is greater than or equal to 0, but it does exist everywhere above the x-axis. All of the decimal values are included, so we're going to write f of x as an element of R beside that. So there's a question here that says, explain why the curve does not appear in quadrant 3 and in quadrant 4. I don't know if you know your quadrant names. We usually call the positive x and y quadrant, quadrant 1, the negative x and positive y quadrant 2 going in counterclockwise direction, and we use Roman numerals normally to designate those. If you don't like Roman numerals, you can just call it quadrant 1, 2, 3, and 4. So this is the starting quadrant, and we go counterclockwise around. So quadrant 3 and 4 are down here. So the reason why the curve doesn't appear there, I'm hoping, is pretty clear. It's because f of x, which is your y values, are equal to x squared. You can't have negative numbers when you square any number. Okay, so any negative number, any positive number put into the function here is going to become squared, and then it's going to become positive, so you can't have any values in the third and fourth quadrant. Now, that's only for this regular quadratic. In grade 10, you see that you can actually flip the parabola upside down, so just keep that in mind. All right, moving on. Not sure how many of you have seen a graph of a root or radical. So let's take a look at this. Again, it says label at least 3 key points, and what I mean by that is table of values. What is the minimum amount of information we would need? Now, because we're square rooting, you can't have negative x's, and that's going to come up in the domain in a second. So I would use 1, 0. Now, the thing is, we get to choose our x values, right? And remember that we're going to be square rooting them. So I'm going to pick 1 for sure, but I'm not going to go to 2, because if I go to 2, I'm actually going to be square rooting something that's going to give me, like a square root of 2 is going to give me some sort of decimal number. So because I can pick whichever ones I want for x, let's pick some that are square rootable. So I'm going to pick 4 and 9. And that's interesting because these x values actually match the y values 0, 1, 4, 9 of our quadratic above. And that's going to be a property we're going to investigate a little later on called inverse functions. When I square root these, plugging them into the equation, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So remember, you're just plugging in x values into the equation, and the f of x, which is your y value, comes from that square root. And again, it's very interesting. I should probably write, this is f of x here. It's very interesting that the x values here are the y values from our graph above, of the x squared graph, and the y values are the x values of the graph above our x squared graph. So there's a switch over of the x and y values from the x squared graph to get the square root graph. And that's something we're going to investigate later on. So when I plot these points, 4, 2, 9, 3, I'm going to get a curve here. Again, very difficult for me to draw the curve properly on my writing tablet here that I have, so I'm doing the best I can. And the graph has a solid point here at 0, 0 and does not continue into the negatives, because you right now can't square root negative values. I say right now because there is a way of doing that, but not on this graph. So we have to write our domain and range, taking that into consideration. For our x values, x has to be greater than or equal to 0, and it can equal 0, as we did in our table, and x is an element of a real number system. For our range, what are our y values, or where do they exist? Well, they only exist above the x-axis, so f of x is also greater than or equal to 0, and f of x is an element of R. Now, one little thing to take into consideration, when you square root a number, you are technically supposed to get a plus or minus value, but we want this to be a function, so we are setting this domain and range, specifically the range, to be a function. There can be a bottom part to this graph, because you get a plus or minus answer when you square root like 1. The answer should technically be plus or minus 1, so you'd have a point above and below. But because we are talking about functions, we are allowed to restrict the range so that we only have the top part of the graph. Similar question to before, why does the graph only appear in the first quadrant? Because you can't square root negative numbers. So we can't have negative x's. They can't be square rooted. I'm just going to write rooted. And does the value of y ever reach a maximum? And if we look at our graph here, we have an arrow at the end of the graph, and that means it's continuously going up as it's going right. That means it never will reach a maximum, because you can basically continue forever for the x values. And that means you can continuously root them. To give the y value. So that might be a new graph if you've never seen it before. This is probably definitely a new graph. F of x is equal to 1 over x. So f of x is equal to 1 over x is a little bit of an interesting graph. So if we do, let's do -4, -1, 0, 1, and 4. And we're going to talk about what we actually need for this graph, because we don't need all of these, but there's something I want you to see here. So if I do, let me just fix this. I always keep forgetting that. If we sub in -4 into 1 over x, that's going to be giving us -0.25, which is a pretty small decimal. If I put -1 into 1 over x, that just gives -1. If I put 0 into 1 over x, I get undefined. What is that going to mean on the graph? And we'll talk about that in a second. And then following the same pattern, we get 1 over 1, which is 1, positive. So it looks like there's some sort of symmetry here. Okay, the signs are different, so it's not exactly the same. And 0.25. So if I plot those points at -4, I'm at -0.25. So let's say right about there. At -1, I'm at -1, which is right there. At 0, I'm undefined. So we'll come back to that in a second. At 1, I have 1. And at 4, I have 0.25. So what does the 1 over 0 do? Well, you can't divide by 0. So you can't actually have any y value along the y-axis. There's no point there. So these two graphs, this one graph seems to be split by that line. And what we're going to do is we're going to draw a dotted line and if you can't see it because it's on top of a dark line on the paper, you can draw it just next to it so that you can see that there's a dotted line there. And that dotted line is called a vertical asymptote. And basically, a vertical asymptote is a line that the graph can never cross vertically, or you can't have a point on that line. So usually that means that the graph can't cross that line because there's no way you can get to that value. So what happens to these two sides of this graph? Well, if I was to go to a decimal value of x, so 0.25, if you divide 1 by 0.25, you'll actually get 4 as an answer, which is up here. So what's happening is if I go to 0.00000001 and I divide 1 by 0.00000001, I don't have a lot of room to write that here. Let me just do this here. Remember, I can pick whatever x value I want, right? The smaller the decimal is here, so meaning the closer I get to the y-axis, the bigger the number gets. And this is usually what happens on an asymptote, is the graph skims along. It never ever touches the asymptote, but it skims along the asymptote. And the same thing's going to happen on this side. If I get really, really close to the y-axis, so negative 0.000001, I should say, you're going to get very, very large negative numbers. So the graph is going to skim along here. Now, what happens when the numbers get really, really big? If I do 1 divided by 1,000,000, the number gets really, really small, but it never ever gets to 0. Okay? Theoretically, at infinity, 1 divided by infinity is theoretically very, very, very close to 0, so we could basically say it's 0, and that's a calculus idea. But really, for us, the graph is just going to skim along here as well. Same thing's going to happen on this side. And that actually gives us a second asymptote. And this is the horizontal asymptote. So from forever on this point, when you see the 1 over x function, I need you to know that there are two asymptotes, a vertical asymptote and a horizontal asymptote. Those asymptotes are going to help you draw this graph. You're also going to use just a few of the values in the table of values then. Because if you know how the behavior of the graph is around the asymptotes, all you really need to know is that on the negative side, you have negative values. At 0, it's undefined. And on the positive side, you have positive values. And that makes the graph only exist in the first and third quadrants. So remembering the asymptotes, remembering these 3 key points right here is going to be enough to be able to draw this graph. So to state the domain, we have to say that the graph exists everywhere, but it does not exist on the y-axis, which is x equals 0. So we basically just say that x can't equal 0, but x can equal any other number besides that. And for the range, we're going to say that f of x also can't equal 0, but f of x exists everywhere besides that. And that's your domain and range. So it says, look at the first quadrant. What happens to the value of y as the value of x increases? Will the value of y ever reach 0? And we've already talked about that. So as x increases, y gets closer and closer to 0. but doesn't reach it. So that's in the first quadrant. So if I go back to the graph here, right here, as x increases, the y value gets smaller and smaller and smaller and smaller, but it never actually reaches 0. And in the third quadrant, it says what happens to the value of y is the value of x. Actually, it should be decreases here. Sorry. And it's the same thing. Same pattern. Y gets closer to 0. I guess we could have said as x increases. I wanted these two questions to match, and I made a mistake, but I guess we could say as the value of x increases, the graph actually explodes to infinity, right? It gets really, really big. If we go back to the graph here. So it gets infinity negative, I should say. So as x increases, it goes down to a very, very large negative number. Okay, but I was wanting to talk about the symmetry as this value of x decreases towards negative infinity, the graph gets smaller and smaller towards the x-axis. And then will the y value ever reach a minimum or a maximum? So when we talk about minimums and maximums, we usually mean along the y-axis. So the graph never ever reaches a maximum because it goes forever in the positive direction, and the graph goes forever in the negative direction down here. So the answer is no, it won't. Okay, let's take a look at this one. By the way, there are 7 of these curves that we're going to take a look at today, and you are going to be asked to memorize all of them. So this is the absolute value function. These straight lines here represent what we call the absolute value. Sorry about that. Again, this is probably a new function for you. I'm not sure if you've ever seen that before. And basically what the, oops, I spelled that wrong, absolute value does is it returns a positive value no matter what sign was in the x value. So that means if you do the absolute value of -2, the answer is 2. If you do the absolute value of +3, the answer is 3. So whatever sign you have in the absolute value symbols, it'll always return a positive value. So we want to sketch a graph of this. So once again, what do we need? Well, the only 3 x values you need for this one are 1 negative value, 0, and 1 positive value to know exactly what it's doing. Because basically, if you took the absolute value symbols away, it would be f of x is equal to x, which is a linear graph. So there's no curves to this graph. And you'll understand why when I start to discuss a little bit more. But basically, if you have -1, it becomes a +1. If you have 0, it becomes a 0. If you have 1, it becomes a +1. So it always returns a positive value. Well, if I plot those 3 points, and then we can discuss what would happen at -2. Well, -2 would become +2. So you're basically just lining up all of these points. And I think after you've seen the graph once, you can remember that. And if I was to draw some lines here to represent the shape of the graph, it gives you what we usually refer to as a V shape here. It does continue forever. So that is the absolute value graph. And the domain for the absolute value graph is, and you'll probably recognize the domain being very similar to a parabola's domain, because even though it's not a parabola, it does basically cover the same 2 quadrants. So x is an element of the real number system because the graph exists anywhere along the x-axis. You're going to have a y value above it, and the range is going to be greater than or equal to 0 and exist everywhere in the real number system. So it's all above the x-axis, which is your greater than or equal to 0, but it does exist everywhere. So that's your absolute value graph. It's a pretty easy graph. Just the problem is remembering it, and these are the 3 coordinates. Just a little bit of foreshadowing. We are going to be learning how to transform all these graphs similar to what was done in grade 10's quadratic unit. Left, right, up and down, stretches and compressions. And that's why you're going to need these tables, because we're going to use the tables to generate our transformations. So that's why you also need to memorize what all the tables are, so that no matter what transformation of graph I give you, you're going to be able to do it. Let's continue with the x cubed. We're almost done. We've got 2 more to do. So for the x cubed function, similar to the parabola, we kind of want to have a few points to be able to tell what's going on with the cube. And generally speaking, I think if we go to -2, we're good enough for the cube function. -2 cubed is -8. Remember that a negative inside of a cube is going to repeat itself 3 times. So -2 times -2 times -2 is going to give a negative value. -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So what does the graph look like? Well, it does have a point at 0, 0, and then 1, 1, 2, 8, and then -1, -1, -2, -8, and you get this kind of stretched out S shape. Again, forgive me, it's very difficult to draw these on my tablet. And then if you went to x equals 3, 3 cubed would be 27, and -27 on the -3 value. So this graph continues forever in both of these directions. So eventually students probably are good enough to just use these 3 to know what the cubic graph looks like, but I do recommend you go to -2, because otherwise it's kind of going to look like a straight line going through 0, 0 here. So the -2 and the +2 just give you that curved look to the graph. Let's do the domain here. The domain is all x. So x is an element of R. And the range will be all y, because it does exist everywhere. Okay, all the y values are present, including decimals. Question, why does this graph only appear in the first and third quadrants? Why doesn't it appear down here or down here? And that's because of the way the cubic value works. So cubing positive values gives positive y values, and cubing negative x values gives negative y values. We've talked about these little quote symbols, meaning repeat the thing that's above it. So that's just the same sentence again, but changing the sign to -x and -y. And our last graph here is an interesting one. This is a graph that actually has 2 variables on the right-hand side, which usually doesn't happen, but we're setting one of the variables equal to 5. Now, the fact that the variables are is kind of a hint as to what this graph is going to be. In grade 10, you probably saw the equation x squared plus y squared is equal to r squared. And I don't know if you remember, but that is the equation of a circle. Sorry about my terrible circle. And if we replace y by f of x and isolate y, you would bring the you'd bring the x squared over to this side, which would subtract, and then you would square root. And that's where that equation comes from. So it is a circle, but you'll notice that it is a square root, which we've talked about before, having some restrictions. And so if we put the r into the equation, you're going to have 5 squared minus x squared, and that is going to be the square root of 25 minus x squared, which you can't do anything with. This is the simplest form of this expression. Okay, don't start thinking you can square root the 25 and the x squared. You can't do that because of the subtraction. So that's the simplest it can be. Now for this one, I actually think, and most people will agree with me, that you only need to know the radius and the shape of the, an example of what the shape looks like to be able to remember what this graph looks like. And basically, this is a graph that is a circle that is only the top part of the circle, so half a semicircle, and the radius is 5, so it's going to touch these points. I'm not going to do a very good job of graphing this, but I'll give it a try. So you have this side of the circle and this side of the circle. So there's your semicircle. All right. And the only thing that would change is if the radius was another number. Let's say the radius was 3, then your graph would be going like that to the 3's. Okay. So your key points here are negative 5, 0, 0, 5, and 5, 0. So those are the key points, and the negative 5 and the 5's come from the radius of the circle. So I think if you kind of have to memorize what the equation looks like, and it's always going to be something like this. They'll either give it to you as I wrote it up here, or they'll give it to you with a number inside of the root like this. Usually it's given with a square rootable number for your r squared. Okay, so if it's 25, you need to know that it's 5 squared. If it's 49, you'd have to know that it's 7 squared. But with a little bit of memorization and practice with this, it shouldn't be too hard to figure that out. So the domain, there is a restricted domain here because this is a starting point and this is an ending point along the x-axis. So this is one where we have to use our interval notation. So we have from negative 5 to 5. Please remember the direction that these point in when we're talking about interval notations of two numbers on either side of the x, and also make sure that the small numbers on the left and the big numbers on the right. That is the proper way of doing this. And then we would write that x is an element of r because all of the decimal values of x between those points do exist. For the range, the graph exists from 0 all the way up to a y value of 5. So again, we do have our interval notation. Sorry, I should probably use f of x here. So f of x is greater than or equal to 0, smaller than or equal to 5, and f of x is an element of r as well. So a little question here. It says predict what the graph of f of x will look like if you have a negative in front, and this is still the semicircle. Okay. So just a discussion here, and this is the level of understanding that I'm hoping you'll eventually have. If you're putting a negative in front of the answer, isn't that going to change all of the y values? Because f of x is a y value, right? So the f of x is going to be the negative of what it normally would be. Well, if the y values are the negative of what they would normally be, wouldn't that mean that the graph would be down here? And because it's 3 squared, we actually know that the radius is 3, so we could figure out those 3 points. And it says check the prediction with the graphing calculator. You could use Desmos to do that. If you type that equation into Desmos, you might be able to, or you should be able to see what the graph looks like, and it should look like this. Okay, so that is your introduction to what we jokingly called, or some teachers that I've talked to jokingly call the 7 deadly curves. Basically, it's 7 functions that you need to memorize the look of and make sure that you can draw from memory. All right. So if I give you the equation right now, what is f of x is equal to 1 over x as a graph? I need you to very quickly be able to say, okay, well, the 1 over x graph has an asymptote here, has an asymptote here, and basically looks something like that. Okay. If I give you f of x is equal to 1/3, sorry, 1/3, my mistake, x cubed. Okay, can you set up the table of values for that? So -2, -1, 0, 1, 2. -2 cubed is 8. -1 cubed, -8. -1, 0, 1, and 8. Okay, how quickly can you generate that table of values? And from that table of values, can you draw the shape of a cubic? Okay, so you need to be able to do that with all of the 7 functions that we saw today. Now, the linear and the quadratic you should be very comfortable with. So really there's 5 of them that you need to learn. So that's the end of the lesson. There will be probably a handout to accompany this. Have a great day, folks, and we'll talk to you soon.